Alright, so in this video I want to look at the reaction mechanism behind the synthesis of acetamide from acetic anhydride. So here on the left, here in our reaction side of things, we have acetic anhydride, and we're going to react this with two equivalents of ammonia, which is going to give us acetamide here, as well as, of course, our other product, acetate anion. So what is the mechanism behind this? How do the substituents here and constituents rearrange to give us our final product? Well, let's go ahead and look at the first step of what's taking place. Well, we have here our acetic anhydride and our first equivalent of ammonia. And what's going to happen here is we're going to attack with this ammonia one of the two carbonyl carbons. Now, it doesn't matter which one because this molecule is symmetrical, so that's irrelevant. But the question that's important to answer is why the carbonyl carbon? Why not any other carbon or atom in this molecule? Well, that's just because. Quick recap here. In a carbonyl, the oxygen is going to be more electronegative. So let's get a little different color here. More electronegative than the carbon, and so we're going to have a partial negative charge there and a partial positive charge on the carbon, which is going to make the carbon much more electrophilic. Okay? So let's go ahead and write out what happens here. First thing that we see is, and I'm going to choose this carbonyl carbon on the left to be our reactive site just for ease of writing. The ammonia attacks right here to this carbonyl carbon. We have that attack taking place. And then this will yield what? Well, we'll have our, I'm going to write out methyl as just Me instead of CH3 just for sake of space here. So we'll have our methyl group, we'll have our carbonyl carbon. But look, if we added the NH3 right here, what's going to happen? We're going to have 5 bonds to carbon. 5 bonds to carbon, not okay. So what we need to do is go ahead and kick some of these electrons from the pi bond onto this oxygen. It will give the oxygen a negative charge, but it will allow us to add the ammonia to that carbon. So now that we've done that, we're okay. We'll draw on the electrons here on this oxygen that we have going on. We have 3 lone pairs of electrons. If I can draw them, we'll have 3 lone pairs of electrons on this oxygen, maybe. Okay. Very difficult today. Not sure quite why. Okay, there we go. And a negative charge. And of course, this is going to just still be connected to an oxygen, another carbonyl carbon. That carbonyl is maintained. And a methyl group. Now, right here, we have attached our NH3. But let's not write it like that. Let's write it out a little bit differently. How about we write it NH2 and put our H on the other side. Now, you'll see why this is important in the next step. Well, if you remember, I said we had 2 equivalents of ammonia. So this was our first equivalent that we used. Now we're going to use our second equivalent of ammonia in this reaction. So let's go ahead and put that in here. Where is this going to attack? Well, you might be tempted to say, well, it'll attack the other carbonyl, right? We'll just go on and attack here. Well, that actually won't happen, because now that we have this here, we can deprotonate the NH3 here by having these electrons attack this hydrogen, and those electrons now will go on to the NH2, and that will give us this product. We'll have our methyl maintained, our carbon here. Alright, we still have our negatively charged oxygen going on. And we have NH2 attached here, carbon, oxygen, carbon, carbonyl, and a methyl group. And of course now we have in solution NH4 with a positive charge on it. So now what's the next step that's going to happen? Well, we still have this negative charge up here on the oxygen. That's not fantastic. We should probably get rid of that. So when we do that, we will reform this carbonyl, reform the pi bond here. And, well, we don't want to make NH2 our leaving group. That would kind of defeat the purpose of what we've been trying to do here. So let's just go ahead and cleave off this entire side of the molecule. Let's take these electrons, kick them on to the oxygen, and this is going to give us the product we'll write out here on the next page because we've run out of room. Now we have our, and I'll write out methyl as a CH3 again. We have our methyl group. We have our carbonyl carbon. It's now a carbon as we reform that pi bond. And it is attached to what? Well, it's attached to NH2. Okay? And what also do we have? Well, we cleaved off this other side of the molecule over here. So now that we cleave that off, it has become an anion, the acetate anion that we talked about earlier. The oxygen, because we put those electrons onto it there, in this step, has a negative charge. And it is attached to carbonyl group, which was never touched, and another methyl group right here. So let's see if this compound is what we looked at in the beginning, and I think it is. So we wanted to synthesize acetamide from acetic anhydride. So we have our acetic anhydride, 2 equivalents of ammonium, and we wanted to get acetamide and an acetate anion, did we? Well, acetamide is exactly what we have here, so that looks good, and this looks like an acetate anion to me, and it is. We have our negative charge here on the oxygen, our maintained carbonyl, and our maintained methyl group. So that's it. We're done. It looks like the synthesis has been successful. So let's do a quick recap. Synthesis of acetamide from acetic anhydride. We have, we'll get rid of all this blue so we can go through it with a highlighter. We have acetic anhydride, 2 equivalents of ammonia. And what happened first? The first equivalent of ammonia attacked either one of these carbonyl carbons. We just decided to pick the carbonyl carbon here on the left for that. And that kicked some electrons from the pi bond in the carbonyl onto the oxygen. It gave that oxygen a negative charge. And this, of course, when we attacked this carbon, it affected the addition of the NH3 group. Well, we did that, but then we deprotonated the NH3 to give us some positive NH4 in solution, and to now just have an NH2, because that's what we wanted. And after we did that, we took the negative charge off of this oxygen in order to reform our carbonyl. We had since we did that, we wanted to not make this guy the leaving group because that would be, defeat the purpose. So we decided to cleave off this entire side of the molecule here, which we did, and that resulted in our acetamide, which we wanted, and our acetate anion. So this was a relatively simple and successful synthesis of acetamide from acetic anhydride.